I'm going to talk about doing some advanced, I say advanced loosely, but doing some 3D seismic visualization in Python and how a lot of the quote, advanced methods actually can be solved really easily with the building blocks that a lot of the scientific Python ecosystem gives us. So we don't need a lot of the very fancy, very expensive tools to do some things that are actually pretty nifty and in some cases even somewhat cutting edge. So on the animation you're seeing right now is basically of something called straddle slicing is what it's called a lot. You're basically just interpolating between horizons and slicing parallels through stratigraphy to a bunch of things. And I'll kind of walk through that and show some examples. So first off, a little bit about me. I'm a geologist or a geophysicist, take your pick. Depends on who you ask. I currently work for oil and gas exploration. I work for Chevron right now, but I'm here on vacation, so they didn't want me to put an affiliation. So they don't want to claim me. But I have a few small Python libraries I maintain. This is actually going to be a talk about the other ones. This is basically a talk about all the crappy code I wrote during my dissertation that actually did some neat stuff. And it's released. It's on GitHub. It has been for several years now, but it's not really in very good shape. So I wanted to kind of simplify some stuff down and show some of the concepts behind it, but not necessarily go over the libraries in detail. So just to give you some idea what I'm talking about, I hate outline slides, but what I want to do is talk a little bit about where the data comes from really quickly, talk a bit about what we're doing, and then I'm going to jump to an Python notebook and kind of walk through some examples. And we'll see how that goes. Those always, I'm hesitant to do this, but hopefully it'll run smoothly. Okay, so let's jump to Japan. I would feel remiss if I did not put a map in here. I am a geologist after all. So we're in Japan. As you may or may not know, there are two subduction zones in Japan. Now, if you don't know what a subduction zone is, don't worry about it. But basically, the big earthquake in 2011, the Tohoku earthquake, occurred in the northern subduction zone, Japan Trench. That's the one we did not think it was going to occur at all. It was actually a huge shock to the earthquake seismology community. The reason is that the Nankai Trough in the south is what was previously thought to be kind of the archetypical, this is a subduction zone that produces giant earthquakes. And because of that, there's been a lot of work done there. So just kind of zoom down on that red box. Two earthquakes, 1944 and 1946, won't talk a lot about. Basically, they decided to focus a lot of work back in the early 2000s, actually starting about 2005, 2006, this project called Mantris Eyes, and focus it in a particular area in the Nankai Trough. So I'm stealing a slide from my advisor here. Mantris Eyes basically is a project to go down and drill deep into an accretionary prism, sample the seismogenic zone, do some really neat stuff. And it's a project I was involved with during my dissertation. But basically, as a precursor to that, they collected a lot of 2D and 3D seismic data. Now, what's really interesting is this is actually industry-acquired 3D seismic data. So it's acquired by I forget if it was CGG or Western GECO, one of the two. So it's industry vendor acquired. It's actually quite nice seismic data. This is, what I'll be showing today is actually pre-stack depth migration that was done at JAMSTEC, the Japan Institute of Marine Science and Technology. For those of you who don't know what that means, don't worry about it, just a processing type. But this is really remarkably nice seismic data. So most of, whoops, sorry. Forgot I changed that order. So what we actually needed, once we had the data, we had a lot of people looking at it. There's 250, 300 people working on this data. But one, there's, when you go into the geophysics world, there's a lot of walled gardens, a lot of proprietary software kind of ecosystems that have very few bridges in between. In our case, we used Landmark Suite, OpenWorks. I did a lot of stuff in Geoprobe as well, but that's part of OpenWorks, just a separate part. We need to get our data out of that. We need to actually be able to analyze it in different ways. So one of the things I did was sit down and reverse engineer a lot of their file formats, just figure them out. They're basically pretty simple formats, so it's not as hard as it sounds. That's Python Geoprobe. It's a library that I learned a lot while writing, which means it's awful. But it does allow you to read and write the files to and from disk, which I'm going to be using to read in the data today. I also wanted some way I could actually use simple scripts to get vector output for publication quality images, and that's something that was really missing from all the really expensive proprietary software we had. Everything in the industry world runs on screenshots. No one cares if it gets published. It's a screenshot. That's all you ever need. You don't ever modify it. So in the academic world, you need something you can bring in, put annotations on that's actually high enough resolution to put on a poster. And you need vector output so you can modify things and tweak it. And so one of the things I did was take and write this nice little library that's giant kludge code. It's called Seismic Plotting. It is on GitHub. It's in bad shape. It does some cool things, though. I'm not going to talk about that library today. What I'm instead going to do is break down and talk about some of the stuff that it does without actually using it. Yeah, I know. Yeah, it's actually not that bad, but it has some project-specific stuff still in there. That was more, I needed to put it on the web to be able to use it from some other stuff that was for a paper. It's a long story. Anyway, most of what I actually do is structural geology. So I'm an interpreter, more or less. And you put something like this up here, you've got to convince someone that what you've drawn at the bottom is actually what's there. This is one of the big things we have. We stare at little wiggles for years, and then we have to convince everyone those little wiggles mean something. So what we really needed, and this is a big regional scale. Most of what I work on are regional and mega-regional problems, especially now I work on stuff on continent scales. But a lot of the stuff, you work on more detailed scale, it's where some neat visualization techniques can really come in handy. So what we really needed was better visualization. And we needed to convince other people of some of these things, particularly small faults right at seismic resolution. I'll show some of those. Some subtle stratigraphic changes, and the overall seismic geomorphology of the area. Now, if you don't know what that means, it just means what it looks like in map view, essentially, so looking down from the top. So to do that, one of the useful tricks, you can co-render an attribute called coherence, which is basically a similarity comparison with the regular seismic amplitude you look at, and it really shows faults well. So I'm going to give some examples of that and some other examples of co-rendering other things. Co-rendering just means blending multiple volumes, multiple different attributes. And then also use some stratal slicing, and I'll explain what that is later on, to kind of show these subtle stratigraphic changes. So let me go ahead and give a quick example of what I mean by some of this. This is actually the seismic plotting library. I mentioned it was so awful. This is actually one of the figures it produces with some annotations at the bottom, so it's not exactly its output, but pretty much is. The key thing, though, is look at the top image. For those of you who don't know what a fault is, don't worry about it, but there are some small faults in there. They're hard to see, and at this scale, it's pretty hard to make out. The middle image, though, is co-rendered. We have some coherence there that basically we've kind of used to highlight the faults. They really show up. You still see the original seismic data. It makes getting someone to believe your interpretation at the bottom, when it comes to the faults anyway, a lot easier. Another thing is the stratal slicing. In this case, it was a lot of back and forth as to what's mass transport, what's not. In other words, where are the landslides, and then where are the channelized features at the bottom. And you can see these very clearly when you do something like this. So those are landslides, and now we have some nice channelized features. It makes getting some of these points across much easier. So let me talk about how we do this. And this is where I hope everything's going to work right. Okay, so what I'm going to do is I'm going to walk through this in small examples. And so to start out with, just for reading and writing data, so give a quick example of Python geoprobe. Basically, we have the data, we can load it in. By default, it's just a memory mapped volume. That's what you're seeing there. And then if we want to actually load it into memory, we can. This is a small volume, so it's only 30, 40 megs. It's quite small.
Did you hide the header in the toolbars?
Yeah, absolutely. Let me do that really quick. Let me just...
I meant the SciPy. I meant the iPad.
Oh, right, yeah. Let's see.
Yeah, I'll header.
Thanks. I should actually probably go ahead and get that out of the way. Well, I should have hit the other one first. No problem. Okay, so one of the things we want to do is take a look at what it looks like. So Mojave is, or Mojave, I guess is how it should be pronounced. I'm never sure on that. Someone please correct me. But is a great way to take a quick look at things like this. So this is a little bit more complex than you might guess. If we just do it, just straight taking the volume in, 3D seismic volume, so it's a 3D array, and just called, let's image plane widget, it'd be upside down to the way the volume's ordered. So we have to do a couple little tricks, but basically we can get something that looks pretty nice with pretty minimal effort. So we have, we can slice through here. This is the Z plane, and then we have, inlines through here. So Mojave is great for taking a quick interactive look at your data, and particularly when you're running different algorithms and look at the output. It's a fantastic way to pull it up very quickly. We might also throw a horizon in there, and I'm showing this mostly because I want to show what the horizon we're going to be using for a lot of other things looks like. And so this is basically an interpreted horizon. It's been auto-tracked and from interpreted pics essentially, and so you're seeing this surface that we're going to work with later. So just kind of keep in mind what it looks like. Okay, so I actually need to close that for it to roll the next thing. One of the things we could do is take that surface and map the attributes onto it. This is a very common thing to do with seismic data. So we're going to take the amplitudes we've been looking at and map them onto that surface. Let me explain a bit more about what this is doing before we go to it. So if you'll notice, all we've done is we've taken, loaded in the data, converted things from kind of inline cross lines, these are model coordinates, into pixel coordinates essentially, and then we indexed it. It's really that simple. NumPy makes this very easy. Now this is basically nearest neighbor sampling. We can do any other sort of interpolation if we like. Map SciPy in the image, map coordinates is perfect for that. But it really makes it quite easy to quickly extract things. So what we get in this case looks kind of awful. So this is the horizon on the right, hill shaded version. That's the attribute extraction. The reason it looks bad, it's picked on a 0. There's not much there. So let's actually look at some other attributes really quick, just for the sake of kind of looking at them. Just going to change this to, say, coherence. Gives me a chance to explain what coherence is. So what we have now is the same horizon extracted with a different volume. This is an attribute that looks at similarity. Where it's white, we're basically seeing very similar traces side by side. Where it's dark, they're less similar. So it's essentially sort of an edge detector, only it's an edge detector comparing the phase of adjacent traces. If you're really interested, I've got some nice examples I didn't put in here to really explain what it is, but we leave it out in the interest of time. So you can see some neat stuff. It's actually a fault right there, another fault there. Won't really get into it. You can also faintly make out some of these channels. Okay. Another thing we can do is to do various types of co-rendering. Now, co-rendering means blending multiple different attributes, multiple volumes into one image, usually using some sort of color. So one of the things I want to put in here is it's really easy to do a crude, simple spectral decomposition in Python. It's just really a few lines. That's it. That's co-rendered spectral decomp, which did I? You know what? I think it's, all right, let's scroll down here. It's what happens when you middle click on a window without realizing it. Okay, so what this is, spectral decomposition is basically a series of closely spaced bandpass filters. All we're doing is, one way to implement a bandpass filter, you may remember, normally you design this a little bit better, but you can subtract Gaussian filters. So we just took a bunch of Gaussian filters, subtracted them, we get bandpass filters. And what we get, it's going to take a second to run, will be a different bandpass filter in each red, green, and blue band. So you're seeing it here. Okay, looks kind of ugly, but it's showing some information. But we can do things like, for example, map that onto a horizon and get a bit more information. So this is that same thing mapped onto the horizon we were looking at before, and notice the colors begin to highlight some of these channels, highlight some of these things. This is something that's actually only available in a handful of tools. There's things like Geoteric, which is fantastic, really nice, very expensive piece of software. Voxel Geo can do this, but it's just a few lines of code. And it usually gets done only at big companies with very expensive software. So another thing we can do is to use some of the things I've shown before to better visualize the faulting. So I'm going to kind of speed through this really quickly. What we really want to do is combine two images. And this is going to take a bit, isn't it? Why isn't it running? Well, okay, there we go. So we really want to combine these two images. There are multiple ways to do that. I'm going to skip over the point about Matplotlib's odd rendering. The obvious way would just be to overlay them, which isn't quite going to look as good. Notice we get something like this. However, what we could do is use hill shading. That's basically co-rendering. We're co-rendering the hill shade with the colored image. So if we apply the same concept, we can exploit light source. I'm going to tell you that's going to look awful. I'm not going to run it. Matplotlib has something to do that called light source. The reason is we need to actually only use a portion of that. So we need to mask part of it out. This is a big, messy piece of code. The reason is light source wasn't really meant to be subclassed. 90% of this doesn't matter. The only thing that does is basically this mask part. All I'm saying is I'm going to leave part of the data out and only co-render a sub-portion. And two, I'm going to use some different blending modes. So these are RGB 0 to 1 floating point volumes, and basically we're just adding and subtracting things. This is basically different modes of overlaying. What light source uses is going to the HSV domain, doing it that way. This does it in RGB, but the end result is it looks a bit nicer. So if we just mask the two out, and we still use what light source normally does. Oop, I've got to run that first. And you know what? This is going to take a minute, isn't it? Come on. Not quite sure why the kernel's still busy, but it is. So, all right, there we go. This ran a lot faster before. I must have a lot in memory. What we see is something that looks pretty crude, but highlights these faults right through here. And if we use some different blending modes, we can get something really quite nice out of it. Show that quickly. Should pop up before too long. When it does, basically what we'll see is the faults nicely highlighted. I'm going to move on down because I have a couple minutes left and talk about some of the straddle slicing and volume flattening. So if that eventually pops up, I'll show it. The straddle slicing, so if you recall that, image that, so there was, it's running other stuff. You recall this, basically what we're doing is we're slicing down. This was the full version, slicing down through multiple horizons, staying parallel to things, and we can really see that well. But there are simpler things that are just volume slicing. So we're going to flatten the volume. There we go. Now it's finally popping up. Well, this is why I shouldn't do these live. Okay, so volume flattening, what we basically do is we take that horizon, flatten the entire volume on it, and then we can quickly scan through. But we're not going to stay parallel to everything. Notice we're seeing multiple bands of reflectors. We're not only staying parallel to one horizon. We can see things pretty quickly on it. It's just a few lines in Python again. Simplest possible case, loop. You can vectorize it, but you shouldn't in this case. Just loop through. Okay, so the other thing we can do is that we're only slicing parallel to one horizon. So we can instead slice in between multiple horizons. So let's take these two horizons. They're not parallel. Instead, what we'll do is we'll create multiple horizons in between just by interpolating vertically. Again, not a whole lot of code. Basically, that's it. We're just taking and using a simple little linear interpolation in between. And then let's do it for 3D. Let's actually map this onto here. So first, let's load data. This is all data loading. Then we can take 50 grids between our two original horizons. So we're gridding 50 horizons in between the two. And then we'll sample the volume at those locations. And we're going to do it smoothly. And what we'll finally get is something like this, where we can smoothly transition down parallel to all the stratigraphy and really see the seismic data. It really illustrates some of these subtle features very well. So to kind of sum things up, one of the nice things about the Python ecosystem is it gives you a lot of common blocks that you can make some fairly complex visualizations in a very short time, and really gives you the chance to play with them and do things that you wouldn't be able to otherwise. So I don't think I have time for questions. Yeah. Oh, okay. All right. Sorry. Thanks.
Yes, so we have 5 minutes for questions. Just raise your hand. I'll come to you with the mic.